Hello everyone, I am Chinmoy Chakraborty, Assistant Professor, Department of Electrical Engineering, Mallabhum Institute of Technology, Vishnupur. Today, I will discuss a topic: importance of swing equation in power system stability. In power system analysis, we all know that the power system consists of lots of devices and those are interconnected to each other. Although the stability at every point must be common for all those devices, and each and every device has their own protection for their transients. Stability of any system can easily be calculated from generation and load side also, which we will discuss in the later part of this topic. In this lecture, we will discuss the following topics, which is what is the power system stability, types of the power system stability, third one is the rotor dynamics, and the most important part of this topic is swing equation, and with the help of swing equation, stability and analysis, and last conclusion of this topic. Now, coming to the first topic, what is power system stability? As we all know, that power system is a very large complex network consisting of various machines like synchronous generators, transformers, switch gears, etc. And most importantly, the stability criteria is here for removal the fault condition and make the suitable and appropriate operation for the whole system. And by definition of the power system stability, we all know that ability of an electrical power system to regain its initial operating position after being subjected to a physical disturbance. Now, before we introduce the stability part, we have to know what is the stable system. As we all know, the stable system is after disturbance no change from its previous operating conditions or its synchronism. And what is unstable system? After disturbance, if the system loses its control or its synchronism, then the system is called as unstable system. While the marginal system is the system is pushed to the edge of the stability no matter how small a disturbance is added to the system. Now coming to the types of power system stability. Power system stability mainly divided into three cases, that is voltage stability, frequency stability and angular stability. Out of these three cases, angular stability is the much more discussable topic, and you can see here it depends on the rotor angle or del. And angular stability can be further classified into three topics, that is steady state stability. It will occur on the system when a small disturbance happened. Second one is the transient stability, that is occurred into the system when a large disturbance occurred into the system. And third one is the dynamic stability, that is also occurred in the system when a small disturbance happened. But difference between the dynamic and steady state stability is that in case of dynamic stability, small disturbance happen periodically, but in case of steady state stability, it's not the periodical case. Now coming to the rotor dynamics, here you can see that mechanical energy or kinetic energy is converted to the electrical energy with the help of alternator or generator. Now we know that the kinetic energy is equals to half of j omega square, where j is the moment inertia and omega is the angular or mechanical speed of the rotor. And with the relation of the electrical and mechanical theta, we know that theta m equals to 2 by p theta e, and if we differentiate this, we get the mechanical speed or angular speed square equals to 2 by p into electrical speed square, which is omega sm square equals to 2 by p omega s square. Now if we put that equation in the kinetic energy, then we get that kinetic energy equals to half m omega s, where m is the inertia constant. In another way, we know that the kinetic energy is equals to G into H, whereas G is the base MVA and H is the inertia constant. Now, if we equate these two equations, we will get M equals to G into H divided by pi into F. Now, coming to the swing equation, here you can see rotor is assumed and the direction of the rotor is anti-clockwise direction. For that reason, torque will be generated on the shaft of the rotor, which is noted by TSH. Due to the mechanical rotation of the rotor and the torque which is generated mechanically at the shaft of the rotor, electromagnetic torque will produced with the opposite direction of the rotation, that is TEM, which is here clockwise direction, and both this torque opposes each other by Lenz's law. So in first case or ideal case, both the torque will be equal when the steady state condition is happening. In case 2, when a disturbance occurred, then both this torque is not equal and the difference will be Tj minus Tb, which is the damping torque and the inertia torque. And the damping torque for worst case, it will be 0, as the damping torque reduces the oscillations. So we assume the worst case when the damping torque is 0. So the only torque is the difference between the mechanical and electromagnetic torque is the inertia torque, that is TSH minus TEM equals to Tj, and we can write the Tj torque is equals to J into d square theta m dt square, which is the acceleration, and J is the inertia constant, as we all know. Now, if we convert the torque equation or mechanical equation into the power equation, now we have to multiply the torque with the omega or the angular speed. So in the previous equation we multiplied with omega sm. Now we will get that Pm minus Pe, that is the mechanical power minus the electrical power, that will give the equation m into d square theta e dt square, where the m is the inertia constant and d square theta e dt square is the acceleration of the rotor. And again we know that the theta e, the electrical degree, that is equals to omega s into t plus del t. If we differentiate this with the second order derivative, now we will get that the d square theta e dt square equals to d square del t divided by dt square. And if we put the value of the d square theta e dt square into the equation 4, then we will get the swing equation, that is Pm minus Pe, that is equals to m into d square del t by dt square. That is the swing equation for a single machine system, and it is very important for stability analysis. Now coming to the stability analysis with the help of swing equation, we all know that for a cylindrical rotor machine, power equation will be EV by X sin del. Now here we assume that del equals to del naught for initial rotor angle, and for steady state condition electrical power will be equal to the mechanical power. If the system goes through a disturbance, let the del will be changed, and the del equals to, here we assume del naught plus del. And now the PE equation, electrical power equation, will be changed by EV by X sin del naught plus del. And if we put the formula sin A plus B, then we will get sin A cos B plus cos A sin B. With the help of this formula, we get the P equals to P max, that is EV by X into the formula sin del naught cos del plus cos del naught sin del. When the disturbance is very small, then the del will be near about 0 or 1, and we know that the cos 0 is 1, so we'll get the Pmax value, that is Pe equals to P naught plus del P del del into del, and this is the new electrical power equation after disturbance happen to the system. Now from the same equation we know that Pm minus Pe, that is equals to m into d2 d del by dt square, and if we put the value of Pe, that is the electrical power, to the new equation after disturbance happen, that is Pe, so we will get equation m into d2 del t divided by dt square plus del Pe del Pe del del into del equals to 0. Now from the previous equation, if we put the value of del equals to del naught plus del, and if we differentiate this, now we will get that m into del square del by del t square plus k into del equals to 0, and if we make k equals to del Pe by del del, then we will get del square del divided by del t square plus k by m into del equals to 0. And if we write this differential equation in the form d square plus k by m into del equals to 0, and with the help of Sridhar Acharya formula we will get d equals to plus minus root under minus k by m, and with the value of the k we can find the various conditions of the stability. And in case 1, if k less than 0, then we will get the value of the d under the root will be positive and equal and real roots. So the graph you can see here with the del t and t, that is increasing of the rotor angle with the increasing in time, but for stability condition it needs to be constant for every time of synchronism, which indicates that at k less than 0 system is purely unstable. In case 2, if we take that k greater than 0, then we'll get the graph like this, and it is clear from the graph that the rotor angle is on the limit of the maximum value and it is oscillating in nature, and this oscillation can be reduced by the damping torque. So at k equals to 0 system is stable. So we can conclude that the stability criteria with the following conditions: when k greater than 0 system is stable and the rotor angle belongs to the 0 degree to 90 degree value, and when the k less than 0, then the system will be unstable and the del value or rotor angle value will be belongs to 90 degree to 180 degree, and when the k equals to 0, then the system will be marginally stable and the rotor angle will be at 90 degree. So the maximum power limit, that is P equals to P max, it is possible only when, that is, the rotor angle del equals to 90 and sin 90 will be 1, so Pe will be P max, but in the practical case it is quite impossible to achieve or get. Thank you everyone for watching this video.